I'm going to give an introduction about the evolution strategy. So, in the first lecture, I mentioned that it is a kind of laterally inspired method. So, we can consider that is a kind of computational intelligence learning algorithm. So, the difference when we talk about genetic algorithm, we learned before as well as the evolution strategy. So I would like to emphasize that when we talk about the GA, I'm going to compare that with the binary genetic algorithm. So when we talk about ES, the evolution strategy, we use the real value parameters. That means when we talk about function of x, function f, that is a cost, and x, that is x1, x2, x3, all of them, they are real value. Say 0.1, this is 1.3, so and so. So real value parameter, and also ES focus mainly on the phenotypic behavior. That means we are going to talk about the real value, and then corresponding to each gene we have another parameter. We call it is the sigma 1, sigma 2, sigma 3, and then so we call this is the strategy parameters. So compare with genetic algorithm, we only have a chromosome, that is x1, x2, x3, so and so. But now when we talk about ES, associated with each x1, x2, x3, we have sigma 1, sigma 2, sigma 3. This is the strategy parameter which give you some guidance. How do we update the decision variables? Yeah, so we will look at that. How do we update the decision variables later on? So once we set up this decision variable and then the evolution process, that is, we have some genetic characteristic. That means we have the crossover as well as the mutation. Yeah, so this is the genetic operation, and later on we will also apply this genetic operation to strategy parameters as well. So that means in each iteration, all these parameters involving x and sigma, they will evolve according to the current value of f. Yeah, okay. So this slide just gives you an overall picture about the evolution strategy, and this is the pseudocode of the ES right here. Yeah, okay. Now, when we start the algorithm, we need to set up counter t, that is 0. That means we are going to start from 0, and then we are going to repeat this process right here up to certain number of iteration, or when the stopping criteria has been met. Anyway, once we have initialized the population, so we have a population, and then that is now we have this line, and then initialize the strategy parameter as well. Again, when we talk about the population, note that we have x, for example, and then we have sigma as well. So in this blue bar, we have x1, x2, so and so. Associated with each x, we have sigma 1, sigma 2, so and so. Yeah, so the dimension of x and sigma, they are compatible. That means right here up to now we have the population p ready. So I just call this is the population 0, that is which involve the decision variable x and the strategy parameter. And then now we have the mu parents, so the population size, that is mu. And the next step, what we are going to do is to evaluate the cost. That means we are going to substitute this x into a cost function we define. So x is a vector, x1, x2, so and so, which give you 12, for example, for the first decision variable, and then the next decision variable, next set of decision variable, or we call this is individual. Yeah, so which give you minus 12, so and so. Okay, now after we repeat this process, we have these information ready. Up to now we have the population, we have the cost, and then now we enter this while loop. So this while loop will stop when the stopping criteria has been met. What it would be, it depends on how do we choose the conditions or the criteria. But now, inside this while loop, we have a for loop. This for loop, that is, we would like to generate lambda offspring. Yeah, so which involve selection, recombination, mutation, and evaluation as well. So in this slide, I'm going to say when I equals 1, that means we would like to generate the first offspring, and then we enter this line, that is randomly select row individuals from the population, and then we come up with this row parent. This row parent, and actually they are some of the blue bars right here, and then we are going to come up with, for example, this is the I equals 1. When I equals 1, we come up with I equals 1. We come up with the first offspring, okay? And then, because once we have this row parents, we do recombination, we do mutation, we generate the first offspring. We repeat this process, and then so because we would like to generate lambda offspring, so we go back to this point and pick row individual at random from the population. When I equals 2, at this point, that is I equals 2, this row parent will be different from the row parent when I equals 1. So based on this green bars, we are going to perform recombination, that is crossover, and mutation, generate the next offspring. We repeat this process, we will have all this row offspring ready. And then now we get to this point. That is, we need to determine what offsprings as well as the parent in the population will form the population in the next iteration, that is pt plus 1. Okay, so that means we would like to generate p1, that is when t equals 1. So we are going to evaluate the offspring and then do some comparison. I will let you know what we are going to do in this block, and then select the individual from the blue bars as well as the red bars right here, and then to generate the next offspring, that is P1. And now if the stopping criteria have not been met, go back to the top, repeat all this process, and then we are going to generate the population 2, population 3, and so on until we are satisfied with the result or the stopping criteria have been met. Okay, so this is the basic concept. So we will stick to this flowchart. We will stick to this pseudocode, and then with some variations. Okay, the variation involve the number of parents, involve the number of the offspring, as well as the way how do we perform crossover mutation. Yeah. Okay, so if you would like to have the flowchart, refer to this slide, and then so that is another explanation of this pseudocode. So I will leave this to you. And in the coming discussion, we will talk about these 5 main components. So initialization, that is the way how do we initialize the population, so that which involve the strategy parameter as well as the individuals, that is the decision variable. Actually, the first step, that is we usually use the random, we generate them randomly. Yeah. And the next one, that is recombination, that is we will have a number of crossover operation which involve the strategy parameters. And then mutation, and so we will have some self-adapt strategy parameter to show you how it works, and then to generate the offspring after the crossover. Evaluation, it is pretty straightforward, that is we fit in the decision variable to the cost function f, and then obtain the cost value. That is exactly what we have done in the previous lectures. Selection, we have 2 stages which involve selection. The first one, that is to select parent for recombination, and then the next one, that is which individuals survive to the next generation. What I'm talking about, that is the first stage of selection. That is right here, select which these parents to perform mutation and recombination. And then the next one, the next selection that is happening right here, that is we are going to select some of offsprings right here and the parents right here to form the next population. Yeah. Okay, so we will learn the details in the next set of slide or next section.